So I just explained the previous functions that we have seen in the previous lessons. They're basically the same, with the exception of this one function here, which essentially is just, you know, and if I have multiple source and sinks, I want to just quickly superposition them without having to just add them over and over again. And I calculate those resulting streamline function values, u velocity values, and v velocity values. That's the only difference. Okay, so what in the previous Python lessons, I've shown that superpositioning free stream with a source and sink, you can obtain objects such as the Rankine oval or a cylinder, right? So, and those shapes, we saw that aerodynamics and the flow around it, and we see like, what does it really teach us? But we want to see this used on a more, application-based level, such as on an airflow shape. So we're be trying to use the superpositioning tech sorry potential flow technique to see if we can model flow around an airfoil. So before we even start with that, let's start with actually creating the airfoil. What airfoil do we want and how do we make it? The first function here is the create NACA airfoil. So this is to create a 4-digit NACA airfoil. Inputs are you have your X array, the from 0 to 1. How do you want to discretize your points? It's just basically just an array of points from 0 to 1 for your x-axis. Then you have the chord length that you desire for your airfoil to be. I believe M refers to the amount of, 1 second, I have to check. I think M refers to the your um the amount of deviation the maximum camber line has to like the um the x-axis. So it's like the amount of deflection, the amount of camber airfoil have. So the larger that the M value is, the more deflection I expect from the camber line. I believe Professor Robinson should have explained what the camber is and why it's important in class, but it's what the M is for. He refers to, I believe, camber line location. So along your x-axis, where is that maximum camber line deflection going to occur? So the M and P value, the first 2 digits of the NACA airfoil value, the 4-digit NACA airfoil value, refers to camber line, camber deflection value and camber like location. So if you have a symmetric airfoil, usually those two first values will be 0, 0. And in our case, we don't want to deal with camber yet, so we're let that be 0, 0. The last two values is important for our case because the last two value refers to the maximum thickness of your airfoil. And at least for me, that would be this value tau. So tau in this case actually just thickness. So once again, it's maximum thickness of the airfoil. And at least in our case, we're interested in modeling NACA 0012 or below 12. So our tau value would be 12. So that's like the thickness, max thickness of our airfoil, about 12%. So essentially, like I said, well, I just set up my variable. So I set up my X variable based on also on chord length. Then I set up my camber line array in case there's a camber line, which there won't be. So once again, if P is not equal to 0, meaning that if there is a camber deflection, you would run through the section to calculate, what is your camber line going to look like now with this deflection, and where's that max deflection located at? But we don't, so we skip straight to the tau value. So T refers to thickness, or basically just the airflow shape, based on your the x-axis. And so we do this, we go through the step, we calculate the math, we get the thickness of the airfoil. Then to get the upper and lower surface, which is the denotated with U and L, you add that thickness or you subtract the thickness from the camber line position. So in our case, because the NACA 0012 is symmetric airfoil, your camber line is 0. Therefore, you just you add thickness on top, add and thickness at the bottom. You have a symmetric airfoil. So let me just resend that link in the chat. Okay. So next step, essentially, this is I think it's average error mean. So it's just essentially taking the error from the actual airfoil versus what we're going to calculate, which we'll get there in a bit. But it's just saying how far off our shape is from the actual NACA 0012 airfoil. All right. Now back to what something we were more familiar with. In the past election lessons, you've probably seen like this step before. Essentially, it's just setting up the flow field, the grids of the flow field. So, I want discretize 200 points. I want my x axis to be this long, my y-axis to be this long. I'm an infinity value. I set up the grid using these three lines here. Then I create the free stream flow via these next three lines, which once again, the three important criteria parameters, u velocity, v velocity, and streamline value, stream function value. And then, all right, here's the next part. Okay. So essentially, I'm just gonna group, um, well, I'll come back to this in a bit. I want to talk about this, which is, as I said before, this is the airfoil, the airfoil parameters that I'm interested in. I want an airfoil with chord length of three units, and then I want no camber deflection. So these two values don't matter because I don't want any camber deflection, so I don't really care about the camber deflection location. But I want my thickness to be 12, and it's 12%, so then I divide by 100. So yeah, that's the NACA 0, 12. I create it using this function. Okay, now I'm gonna jump back to this part here. Establish source instancings. So essentially, if you remember back to the Rankine oval, we had a source followed by a sink in your free stream. When you introduce a source, the Rankine oval starts to expand, right? That's like the starting point of the Rankine oval starts to expand. It's expanding because of the source. Then after the halfway point, you introduce the sink, and the influence of the sink starts to beat the influence of the source. And when the sink is introduced, you'll see that the Rankine oval then starts to close in until reaches the second stagnation point. So the way that I view it is, if you see our sinks can be used to essentially expand on your geometry, whereas sources are used to expand your geometry, whereas sinks are used to basically shrink or close off your geometry. So the way that people look at it is, if your geometry has positive slope or the slope is increasing, you want to have sources to basically influence that increase in the slope. Whereas if your geometry has slope that is negative and closing, you want to introduce sources or sinks at those locations to close it off. I might have misspoke because I wasn't paying attention, but essentially sources when you see positive slope, sinks when you see negative slopes. That's how they're used. So I want to establish a line of sources and sinks along my geometry to basically recreate that shape. And once again, it's based on the slope of my geometry. That's why you see here I have the dy dx term, which represents the slope. So essentially, I believe the math to create the math sources, or to create your sources, is just that source strength Q is equal to 2 times u infinity times the slopes. But I'll double check the math. Then I plotted a figure to show that based on my array, what is the source and sinks looking like. So let's just show that first thing first. So here's this. So the first image here, y-axis is source strength, and x-axis is the airfoil length from 0 to the chord length. So because of the very, very sharp slope introduced with airfoil from going from basically nothing, 0, to just suddenly jumping up, you have very, very high source strength all the way up to about this point here, like third of the way through the airfoil. Then afterwards, you drop below 0, and the rest of the airfoil has sinks to capture the negative slope of the airfoil closing in to the trailing edge. However, if we were to sum up all the source and strengths, you'll see that you'll get a non-zero answer. So, this is not good, because our final sum here is a positive value, meaning that we're creating more flow than we're destroying. Therefore, the flow will be more non-physical than it should be. So usually the method that I showed was the math, creating source and sinks, looking at the slopes and doing the math. It is much better for completely object symmetric along the x-axis and y-axis, such as an oval or an ellipse or a cylinder. So with a neck airfoil, it's going to struggle. This method's going to struggle. But that being said, I was still able to do it so that I basically decrease the amount of points that I'm using. And for example, using trim to 0, I was able to basically isolate certain points that I'm interested in that have the highest influence on airfoil, and then basically tweak the source and sinks so that the values actually end up equaling 0 when you sum them up. And doing so, I then plot it and look at the result I get in the end. So by just using these five, I guess, two sources and three sinks, I'm able to closely replicate the NACA 0012 airfoil, right? Um, so yeah, this code definitely needs to get worked on, but as you see, the red line is the contour lines that are based on the flow field. It's based on the potential flow itself, whereas the black line is the actual geometry itself. Okay, so if you look at ah, so let me print this. So based on the shape that you see here, which the black line being kind of like the experimental data or the one we're trying to match to, and the red line being our results, you see that the difference or the error based on that error code I showed earlier is about 1%. So it's just a 1% difference between ours and the actual airfoil. Okay, now the next step is just the exact same as what we've been doing in previous lecture, which is that we're taking the contour line, the red line, and we want to solve for the pressure distribution across it. So you know how, once again, to solve for pressure distribution, the steps are really straightforward. First, we isolate the parts we want. We don't want the long red line at y equals 0 because the values are irrelevant to us. We just want the airflow shape itself. So we isolate based on this tolerance value, and we take basically only positive y values is what we're interested in. I just want to look at positive y values. Then, from this SciPy toolbox, which is really important, we're using this ever since the first lecture for our lesson, we use the regular grid interpolator, which essentially is we're creating a function in which we can then plug in x and y values from our streamline, the red line, to basically predict the u and v velocities associated with those points. So with these two lines create the function, and these functions are shown right here with two inputs, y and x, which is obviously because we're in a 2D Cartesian grids. Those are only two inputs. Then we're going to fill in those inputs with x and y based on the red contour line, the red streamline values. And I guess before we move on, the x and y values associated with that red line, I have plot here. This is the approximation based on our potential flow solution. As you see, you initially see like that NACA shape, but it doesn't like smoothly come to a close at the trailing edge. It sharply cuts off right here, kind of like the Rankine oval or like the cylinder. So the shape itself is not great, but this is close enough to what we're trying to do. So we put in those values to obtain the associated u and v velocities. Then we don't want just the velocity components, we want velocity magnitude. Velocity magnitude is what's being used to calculate coefficient of pressure. So I square both velocity components, sum them up, take the square root, essentially just doing hypotenuse or solving for the hypotenuse, Pythagorean's theorem. Then I calculate this coefficient of pressure based on this equation that I've shown before in my slides. Then, well, you saw this earlier, but this part here, I plot the pressure distribution based on x. So here is what you see. Based on our potential flow solution, let's start with this. Based on our potential flow solution, we're going to see that the coefficient of pressure is insanely negative. Then it starts to taper down around here, 0.5, when x goes 0.5. So it's like a sixth of the way to the trailing edge of the airfoil. Then it kind of steadies out. And you see a little bump here, and it drops off again. So if we look at actual data for the NACA 0012, or the NACA 12 airfoil, you'll see that actually we expect at the trailing edge of the airfoil, it should be positive because that's where the flow collides with the airfoil. So we expect positive pressure. Then the flow quickly jumps, and this jump implies basically your flow is accelerating. So the flow quickly accelerates, going to negative, then it starts to decelerate as it goes back down for the rest of the airfoil. So that's kind of like the trend we expect for a NACA 12 airfoil where the angle of attack is 0. However, in our case, ours starts insanely negative, then it drops down and tapers off. So essentially, that first part is like the first part of these plots are not the same. And I guess, why? Well, I guess first off, potential flow is not the best way to model anything like more complicated than an oval or a cylinder. At that point, the physics starts to break off because it's much more complicated than that. The main reason being I believe is um the stagnation points. So we've used the term stagnation points a lot. Essentially, it's where your free stream flow and your source, they basically clash together, and obviously there's like positive velocity from your free stream, and then the source is pushing back with the same velocity at a different direction. So there, your velocity there cancels out and becomes zero. So stagnation points have velocity of zero, and that doesn't really make sense. Those points are kind of like singularities in your flow field. So, and then when your flow of zero at the stagnation point then jumps to a physical value, like a flow of actual value, so a non-zero flow. So therefore, that jump in value causes this tremendous spike in the CP value, just going from very, very positive or very, very negative all of a sudden. Okay, but that is basically what I wanted to show, is that while we can kind of capture the pressure distribution around an airfoil, this method, the potential flow method, cannot keep up with actual airfoil shapes. So what can we do? There's a way to Professor Robson's basically starting this lecture now in class. It's called panel source method. Essentially taking the concept of source and sinks, using source to basically expand your geometry and sinks to close off or shrink your geometry. We can then create basically code and matrices to solve for what we expect each panel to have in terms of like the source strength um, of these panels, and then um, solve them to get the associated U and V velocity components. And the results from there are much better than potential flow. And that's what we're gonna look at in two lectures. Like on Halloween, I'll do another Python primer where I talk about that, because essentially that's really important. That is basically the fundamental logic that's being used for Xfoil, for example. So obviously you see it's being used in Xfoil. And we will basically capture a better CP shape than what you see here right now. Okay, that's the end of my lesson for today. Is there any questions from the audience?
I have a quick question.
Yes, James, what's up?
When you were doing I guess the NACA 23012 airfoil simulation in the lower plot, I saw that you only had the upper half of the airfoil. Is that because you're just isolating the upper half of the airfoil and analyzing it? How
Yeah,
come there's
so
like not the bottom?
okay. Yeah, so we're not looking at the 23012 airfoil. So
Mhm,
obviously, as you said it, it's 23012, right? So the first two terms refer to
mhm,
camber deflection and camber location value.
mhm.
Um, and obviously, if that's the case, your upper and lower surface is going to be different, because obviously those airfoils have camber, and as Professor Robinson explained, airfoils with camber will by inherently just have lift, or maybe negative downwards lift, one of the two. This case here, I'm avoiding any terms of camber line. So because I'm avoiding anything with camber, I have a symmetric airfoil. My flow field has zero angle attack. Therefore, both sides of the airfoil is going to be the exact same.
Okay, I got it. Thank you.
Yeah. Okay. Yeah. So if I was looking at the airfoil you're talking about, that would not happen. Um, I have to do way more math, and I didn't have time this week to even. I actually wanted to do that. I thought it'd been pretty cool. Yeah, but I didn't have time to really work through that, and I tried to initially run into a lot of issues. Maybe next year I can improve this lesson. Yeah. Any more questions? I thought I saw Ryu said something.
Yeah, do you mind going over again why it is that the pressure distribution for this potential flow solution doesn't match up with the actual solution for like say panel method?
Okay. Yeah, definitely. I'll cover that more in detail in 2 weeks, but I'll run over basically the logic that I have that I use. So here's actual validation data based on, I believe, yeah, NASA Lang last lab, yeah, NASA Langley's lab. I believe it's NASA Langley's lab. Yeah. So NASA Langley's lab. And essentially I just see obviously 0 to 1, that's your location along the chord. So at location 0, which is the leading edge of your airfoil, coefficient pressure is positive. So it's positive, right? Essentially,
Mhm.
the reason it's positive is CP, you're tracking stag static pressure. And so at the leading edge, what's gonna happen is your flow crashed into your airfoil. There's not your airfoil does not have a source in it that's pushing back with some velocity. Um, and then so physically the free stream crashed into your airfoil, and that kind of like impact effect is going to cause pressure on your leading edge. So that's why you see a positive leading edge value, positive pressure value at the leading edge. And then this well, from what we see from the plot, the pressure is jumping up, right? However, because our axis is flipped, what's going on is the pressure value is quickly decreasing. So this pressure value is drastically dropping. And that drop in the pressure value corresponds, because once again, we're looking at static pressure. Dropping static pressure means that there's actually a jump in your dynamic pressure. So the flow is speeding up around the curve of the airfoil. And it's speeding up through the adverse pressure gradient. It's kind of backwards. But yeah, like in that section of the leading edge, your flow speeds up. And then as it's tapering down, your flow is deaccelerating as it's going from, I believe this area should be like the maximum thickness area, somewhere around here is maximum thickness. Then it starts to taper off and deaccelerate as it gets to the trailing edge. So that's kind of like the physics of the physical airfoil itself. Okay, but that being said, in our thing here, we at the later segment of the airfoil with the potential flow method, we do see that deacceleration effect with the exception of this only part here, that jump. That's because the airfoil because our flow tapers off too quickly, as you see in red. It just tapers off like an oval. It doesn't go all the way to the end of the trailing edge. But regardless, we see that tapering off effect of the flow kind of like deaccelerating. The only main issue is that leading edge part. The leading edge part, we see a drastic negative CP value, and we don't see any positive CP value at all, right? We're missing that. We expect it to start somewhere down here, then go up a bit, then drop off, then taper off. But it just starts somewhere super high up in a negative value. And the reason why it's starting off in a super negative value is, like I said earlier, it's that stagnation point. That stagnation point, it's non-physical. While it has meaning to us in regards to potential flow, it's non-physical because velocity equals 0 there. And you can't really capture anything. So that non-physical part of the flow results in this flow being very, very different. Does it answer your question?
Yeah, that makes sense. Thank you.
Yeah, no worries. I'll take any more questions, but if not, I have I'll be in person, Kemper 1127. I'll only be there from 3 to 3:30 though. I actually have a meeting at 4 that I didn't realize. So I need to maybe I'll go up to like 3 to 3:40, but I'm only there for 40 minutes. Then I'm gonna ask you guys to leave because I need to take that meeting. But if not, I'll see those of you who come in person, I'll see you in person.
Thank you so much, Hui. Have a good day.
Sweet.
No worries.
Thank you. Have a great
Thank
day.
you. Have a good day.
you.
Thank you.